Think of 3IATLAS as the cosmic tourist who didn't book return tickets or a hotel. In the bureaucratic language of astronomy, it's the third confirmed interstellar object to wander through our solar system, following 1I Oumuamua in 2017 and 2I Borisov in 2019. Interstellar here isn't a vibe, it's a diagnosis. The object's path through space is hyperbolic, meaning it's not gravitationally bound to the sun. Trace its trajectory backward, and it doesn't loop around like a planet or a garden variety comet. It comes in from deep space, pays a brief visit, and heads back out again like a cat that tried your house once and decided your snacks were subpar. So why do astronomers care? Because an interstellar object is literally a sample of somewhere else. Our comets and asteroids are postcards from the early solar system. An interstellar comet is a postcard from someone else's early solar system, complete with coffee stains and weird stamps. It's ices and dust grains condensed around another star, under different temperatures, radiation, and chemical soups. When sunlight warms those ices and makes them vent gas and dust, the coma and tail become a spectroscopic confession. Molecules announce themselves in thin, glowing lines, like barcodes for chemistry nerds. If the lines match familiar solar system patterns, we've learned that planet building is comfortingly universal. If they don't, we've learned that nature has a broader menu than our local takeout. Either way, the universe drops data. We pick it up. Now, about that alphabet soup of a name. 3I tags it as the third interstellar visitor. Atlas credits the Asteroid Terrestrial Impact Last Alert System, the Wide Field Survey that first spotted the faint, moving smudge and rang the bell for follow-up observatories worldwide. In July 2025, the object upgraded from suspicious traveler to definitely not from here, as more positions were measured and its orbit solution snapped into hyperbolic focus. It's the celestial equivalent of checking the license plate and discovering it's registered in another galaxy's DMV. Okay, not literally, but the dynamical evidence is that strong. Interstellar also has a speed component hiding in the math. Imagine rolling a ball past a campfire. If it's too fast, the fire's warmth won't slow it enough to keep it nearby. Likewise, 3IATLAS cruises in with a hyperbolic excess velocity. After you subtract the sun's gravity, it still has leftover speed. You can tweak trajectories a bit with planetary flybys, but you can't fake a permanently unbound path without arriving already primed for escape. That's why the interstellar label doesn't depend on how flashy the coma looks or whether the tail is Instagram ready. It's about the energy ledger. Universe says, books balanced, object not captured. Yes, gravity is the original accountant. If you're picturing a cinematic fireball blazing across the sky, tap the brakes. Objects like 3IATLAS are usually subtle to amateurs and thrilling to professionals. The astrophysical version of a rare bird sighting that looks to everyone else like a slightly different sparrow. What has observers leaning forward is the chance to watch a foreign-born comet turn on as it approaches the sun. As heat seeps in, volatile ices sublimate, building that fuzzy atmosphere and tail. Early images showed the coma growing and the tail developing. Classic comet behavior that paradoxically makes the object even more valuable, a controlled lab experiment we didn't have to build. The sun provides the heater, astronomers provide the thermometers. And yes, the sun does this pro bono. Why is the third one such a big deal? With a sample size of 1 Oumuamua, arguments go in circles faster than a racetrack electron. With 2 Borisov, we could at least say, okay, some interstellar visitors really are comets. A third gives us our first hint of patterns versus quirks. Are interstellar passers-by typically icy? Do they share common ranges of color, dust production, or gas chemistry? Do their arrival directions cluster in the sky in ways that tell us about stellar motions and ejection mechanisms in other planetary systems? The leap from anecdote to dataset has to start somewhere. And equals 3 is better than n equals shrug. Science adores a trend line. It hates being catfished by coincidences. There's also a bigger philosophical hook. Interstellar objects are not just rocks, they're messengers of process. Their very existence implies that planet-forming systems often fling debris into deep space by migrating giant planets, chaotic early dynamics, or passing stars stirring the pot. Every visitor we characterize tightens our models for how common planetary systems are, how they evolve, and how the leftovers travel. If the Milky Way is a kitchen, these are the crumbs you find on the floor that tell you what was baked last week. Spoiler, probably not gluten-free. The more crumbs we analyze, the more confident we get about the recipe list for worlds. And yes, the alien probe question lurks in the background, like the friend who always asks whether the Wi-Fi is secure. It's healthy to keep extraordinary possibilities on the table, right next to extraordinary skepticism and the napkin labeled testable predictions. For an opening chapter, though, all we need is this. 3IATLAS is on a one-and-done solar system fly-through from beyond our neighborhood, and that alone makes it worth every telescope hour we can spare. Nature rarely ships us samples from other star systems with free delivery. When it does, we unbox carefully, we label meticulously, and we resist the urge to write a sci-fi plot twist before the spectra are in. Cliffhangers are for the end of episodes. Claims are for after calibration. Next up, we'll rewind the discovery tape. How all sky surveys caught this traveler. How is that a smudge becomes call everyone. And why automated algorithms are the unsung heroes of late-night astronomy. Astronomers, professional night owls who play Where's Waldo with the universe. Except in this version, Waldo is faint, moving, and only shows up a few pixels tall before vanishing behind moonlight or cloud cover. Enter the ATLAS survey, the Asteroid Terrestrial Impact Last Alert System, whose day job, night job, is to scan the sky every clear evening from multiple small telescopes, looking for anything that wasn't where it should be yesterday. ATLAS lives on cadence. It images the same patches of sky repeatedly, compares fresh frames to a constantly updated template, and hunts for transients, streaks from satellites, flaring stars, sneaky near-Earth asteroids, and on rare, goosebump nights, an interstellar object tiptoeing across the background. Here's the choreography. Each ATLAS telescope sweeps huge swaths of sky with a fast, wide-field camera. Think security camera for the cosmos, optimized not for glamour shots, but for coverage and speed. The hardware is teamed with software that subtracts yesterday's deep image from tonight's fresh one, pixel by pixel. Most subtraction discoveries are noise, cosmic rays smacking the detector, hot pixels that won't cool it, or airplane glints pretending to be astrophysics. The pipeline triages these by shape, brightness change, and motion. Real celestial visitors don't just blink, they move consistently from frame to frame. A genuine moving point leaves a breadcrumb trail across the series, and that's when the alert sirens chirp quietly. This is astronomy, not a submarine movie. Automation is essential because the sky is a brutal data firehose. A single night yields tens of thousands of candidates. Machine learning filters and hand-tuned heuristics act like seasoned bouncers. Star, you're on the list. Hot pixel, you're not. The survivors get promoted to a tracklet, a short sequence of positions and times that describe a coherent motion. From a single tracklet, you can't nail an orbit, but you can predict where to look minutes or hours later. That quick follow-up is the difference between cool blip and new object with a paper and prep. The universe, like a cat with a laser pointer, refuses to hold still. Once a curious mover pops up, the ATLAS team fires off notices to a global network. The Minor Planet Center, MPC, is the central switchboard. Observers worldwide snag coordinates and pivot their telescopes to chase the newcomer. Confirmation isn't a ceremonial stamp. It's a statistical ritual. Independent observatories must see the same thing at the expected place and time and measure positions precise enough to shrink orbital uncertainties. If the reported path keeps bending toward hyperbolic, Eyebrows rise, not aliens at 5 o'clock rise. More like, okay, this is getting spicy rise. Precovery is the unsung hero of discovery stories. After an object is announced, astronomers comb through archival images from surveys like Pan-STARRS, ZTF, DECAM, and others, hoping the visitor photobombed some field days or weeks earlier. Those serendipitous cameos, once measured, extend the observational arc backward in time and transform a fuzzy orbit into a crisp one. It's like finding old security footage of a suspect strolling past 3 other cameras. Suddenly, their route makes sense. Precovery often also pushes the brightness record to fainter magnitudes, revealing when the activity switched on and how fast the coma grew. Tiny details that later drive big inferences. Let's talk sky scanning logistics, the place where romance meets spreadsheets. Surveys juggle seeing conditions, moon phase, and weather forecasts. They prioritize fields near the ecliptic for asteroids, then throw in high-latitude swaths to catch oddballs. Exposure times are short enough to freeze motion, yet long enough to pull up faint points from the noise. Astronomy's Goldilocks zone. The cadence, how often a patch is revisited, enables the motion check. 4 images separated by, say, 10-20 minutes form a classic quad, just enough time for a nearby rock to budge a few arc seconds, while distant stars stay put. Plot those dots, fit a line, and you've got the seed of a tracklet. Plot 2 quads an hour apart, and now you can sniff acceleration from Earth's parallax, an early hint of distance. Once the MPC posts early astrometry, orbit wizards swoop in. Initial solutions are preliminary, because small measurement errors balloon over time, like an untied balloon at a birthday party. But even that shaky first fit can whisper whether the path is closed, barely open, parabolic, or emphatically open, hyperbolic. For a potential interstellar object, the watchword is caution. Comet outgassing can fake a touch of non-gravitational push, and measurement biases can impersonate escape velocity. That's why the confirmation phase stretches across nights and hemispheres. Northern and southern sites trade baton passes to keep the sky relay going while the Earth spins. Physics doesn't nap. Telescopes shouldn't either. Meanwhile, photometry rides shotgun with astrometry. As observers collect positions, they also measure brightness in multiple filters. If the object brightens faster than geometry alone would predict, it hints at active outgassing and dust production. Conversely, a steady faint point might be inert or just far away. Color indices, differences between filter magnitudes, start sketching personality. Neutral, reddish, dust-rich, gas-poor. No one writes a biography from this early teaser, but first impressions steer which instruments are begged for time next. Narrowband comet filters, higher resolution images, or even spectroscopy if fortune smiles and the object isn't too dim. False positives deserve a moment in the spotlight because they teach humility. Satellite glints can mimic motion in back-to-back frames, so can high-altitude airplanes, meteors, and the occasional was that a moth artifact. The defenses are geometry and redundancy. Real celestial motion aligns with sidereal coordinates, not local horizon quirks. Real objects persist across independently timed exposures and, crucially, reappear the next night at a position the provisional orbit predicted. Nature might be playful, but it's rarely that coordinated by accident. Once cross-observatory confirmation lands, the tempo changes. Circulars go out, telescope proposals multiply, Slack channels populate with finder charts and exposure calculators. The discovery team hands off to a broader community with specialized instruments, bigger apertures for deeper imaging, high dispersion spectrographs for gas fingerprints, polarimeters to probe dust grain alignment. The baton pass is ceremonial, but the reason is practical. The sky clock is unforgiving. A visitor on a fast, outbound trajectory fades rapidly, and every night of dithering is a night of permanent ignorance. Astronomy is a sport where use it or lose it is not a motivational poster. It's the rule book. Zoom out, And the recipe for catching an interstellar gatecrasher looks simple. Scan wide, scan often, subtract smartly, alert quickly, confirm globally, pre-cover ruthlessly. The magic is in doing all of that, every clear night, without blinking, while the sky throws curveballs, the moon hogs the spotlight, and the data pipeline insists all gremlins arrive 10 minutes before sunrise. It's messy, it's relentless, and it's weirdly beautiful, because every so often, amid the false alarms and cosmic photobombs, a faint speck moves just so. The numbers refuse to lie, and you realize you're watching a traveler from somewhere else slide across your CCD. Waldo found. Now the real work begins. This orbit screams, "I don't live here," louder than a tourist in socks and sandals. To see why, we need to open the cosmic geometry toolkit. In the sun's gravitational field, every path a small body can take is one of 4 conic sections: circle, ellipse, parabola, or hyperbola. Circles and ellipses are the comfy apartments of bound residents. Negative specific orbital energy, predictable rent, always coming back around. A perfect parabola is the razor's edge between bound and unbound. Exactly 0 specific energy. Think of it as couch surfing on escape velocity. A hyperbola is the road trip that never loops back. Positive specific energy means you're not just leaving, you arrived pre-approved to exit. Interstellar visitors clock in with an eccentricity comfortably above one once enough observations pile up to crush the uncertainties. That value isn't a vanity metric. It drops directly out of the positions and times measured over nights and weeks, as the object traces a slice of its path around the sun. Fit the trajectory, get E, and you've essentially read the stamp on its passport. You might ask, couldn't a clever series of planetary flybys juice a bound object into a hyperbola? Planetary slingshots are indeed nature's coupon codes for velocity. But there's small print. In a gravity assist, you steal a smidge of orbital energy from a planet by diving through its gravity well. The assist changes your velocity relative to the sun, but the budget is capped by the planet's own orbital speed and by geometry. Jupiter, the heavyweight champion, orbits the sun at roughly 13 kilometers, Earth at 30 kilometers. Even under ideal angles, the energy boost for a small body starting on a bound orbit can inch you toward a near parabola, but it's brutally hard to convert a domestically born rock into a confidently hyperbolic escapee with meaningful VVIN. It's like trying to push a grocery cart to highway speed by sprinting and jumping on. You'll go faster, but there's a ceiling before physics files a complaint. There's also the Tisserand parameter, a quiet accountant that keeps track of the relationship between a small body and a perturbing planet, often Jupiter. For a bound comet roughly controlled by Jupiter's influence, the Tisserand parameter with respect to Jupiter, TJ, hovers in certain ranges. If an object shows up with a TJ that makes no dynamical sense for a native, like a tattoo from a club we don't have in town, you start suspecting it didn't grow up under Jupiter's rules. Interstellar interlopers don't obey the local Tisserand bookkeeping because their initial conditions were set by another star's disk dynamics, not ours. What about the classic confusion? Parabolic-looking long-period comets from the Uti cloud. Those often have Eyork extremely close to 1 and arrive with speeds just brushing the local escape velocity. With modest uncertainties, an early orbit fit might flirt with ATIA slightly above 1. But as the observation arc lengthens, most natives collapse to barely sub- or super-parabolic solutions consistent with being bound before solar tides, and planetary nudges modified their path. An unmistakably interstellar case, by contrast, retains a decisively positive V8 after weeks of astrometry. Its hyperbolic excess doesn't evaporate with better data. If the number refuses to trend to 0, you're not chasing rounding errors. You're watching a visitor with foreign inertia. Let's also address non-gravitational pokes, things like outgassing forces from sublimating ices, or a feathery radiation pressure push on tiny fragments. Those can tilt orbits, sometimes nudging the eccentricity if you fit the data assuming pure gravity. But astronomers account for this with non-gravitational force models that add parameters for thrust-like effects proportional to the heating curve. If you need a heroic, finely tuned jet model to fake a sustained V, the data will protest. In addition, non-gravitational effects are most conspicuous near perihelion and fade with distance. A true hyperbolic excess remains visible even when the heating and any outgassing has calmed down. There's also frame of reference hygiene. Astronomers often transform from heliocentric to barycentric, solar system center of mass frames when pinning down Vivigny, because the sun jiggles thanks to planets, mainly Jupiter. A real interstellar trajectory is unbound in both frames once you propagate far enough out. If it only looks hyperbolic in a poorly chosen frame, or during a brief arc near perihelion, suspicion is warranted. But if the unbound verdict survives frame changes and time, that's not a quirk, it's identity. Finally, consider where hyperbolas point. Bound comets tend to cluster around source regions and are sculpted by planetary perturbations. Their incoming directions reflect our cloud and our planet's long arm. Interstellar visitors, by contrast, paint arrival vectors that mirror the sun's motion through the local stellar neighborhood and the kinematic soup of nearby stars. When you plot that motion and the object's phi v, the numbers whisper, "I started life under a different star, got ejected by gravitational pinball there, then coasted for eons before catching your sun's eye." In other words, socks, sandals, and a suitcase plastered with stickers from places we don't have on our map. Coma and tail, nature's way of saying some assembly required when ice hits sunlight. A bare nucleus, typically a few hundred meters to a few kilometers across, looks like a charcoal briquette lost in a snowstorm, dark, low albedo, and radiating heat grudgingly. The magic starts when insulation warms volatile ices buried near or beneath the surface. Molecules transition straight from solid to gas, sublimation, dragging dust grains with them through fissures and vents. The immediate result is a thin, expanding atmosphere around the nucleus, the coma. Give it a bit more sunshine and a headwind from the solar wind, and that atmosphere gets combed into tails plural, because dust and ions have different hair days. Not all visitors put on this show. An active comet is one whose ices are accessible enough, and the sun close enough to drive sustained outgassing. An inert rock, think many asteroids, lacks appreciable volatiles or hides them so effectively that even perihelion can't tease them out. The boundary isn't a legal category so much as a spectrum. Some objects only spritz at very small heliocentric distances. Others start hissing far out, where only ultra-volatile species, carbon monoxide, CO, and carbon dioxide, CO2, can sublimate. Water ice requires more warmth, so H2O-driven activity tends to ramp up closer to the sun. Translation: different ices have different thermostats, and the coma is your thermometer with a flair for drama. Sublimation is a balancing act between absorbed sunlight, thermal re-radiation, and the latent heat required to turn solid to gas. If energy in exceeds energy out by enough, molecules escape the surface. If not, they sulk in solid form. Surface texture matters. Dark, dusty mantles soak up sunlight and insulate underlying ice, creating pressure cookers that burst open as jets. Bright, fresher patches reflect more light and can chill themselves into quiescence. Rotation adds spice. As active areas rotate into daylight, the coma breathes, diurnal pulses that can imprint a heartbeat on brightness curves. Think of the nucleus as a barbecue that spins. Some steaks get seared, others stay rare, and the smoke, gas plus dust, rises in intermittent plumes. The coma's physics is a story of collisions and chemistry. Close to the nucleus, the gas is dense enough for frequent bumps. Molecules thermalize toward a local temperature, and dust grains experience drag that lifts them off the surface. A few tens to hundreds of kilometers out, depending on production rate, collisions thin out, gas expands ballistically, and dust decouples, coasting under gravity and radiation pressure. Dust sizes matter. Pebble-scale chunks stay near the orbital plane, forming a thick, stubby fan. Micron grains get bullied by sunlight, feeling a force comparable to the sun's gravity, scaled by beta, the radiation pressure parameter. High beta grains are flung into the classic curved dust tail, while the biggest grains lumber along like stubborn mules. The ion tail is a different beast, straight, narrow, and moody. Ultraviolet photons and charge exchange reactions ionize cometary molecules, CO, H2O, and their photodaughters. Once ionized, these species couple to the interplanetary magnetic field embedded in the solar wind. The result is a tail that points roughly anti-sunward, but can kink, ripple, or even tear during solar wind disturbances. When you see a sudden disconnection event, a tail segment peeling away, you're watching space weather graffiti on the comet's canvas. Dust tells you about surface dirt and mechanical lifting. The ion tail tells you about upstream plasma and photochemistry. Two tails, two diagnostics, one dramatic hairdo. Chemically, the coma functions as a portable lab. Parent volatiles vent directly H2O, CO2, CO, NH3, CH4, etc. But many of the gases you see at optical wavelengths are daughters, fragments produced when sunlight breaks parents apart. CN, C2, and C3 are classic optical tracers, not necessarily primary ingredients, but reliable neon signs for underlying organics. In the near-infrared, you can catch vibrational bands of H2O and CO2. In the radio and submillimeter, rotational lines from CO. Each species has its own volatility and photochemical lifetime, so the radial profiles of brightness become fingerprints. Steeper or shallower fall-offs hint at whether molecules are emitted directly from the surface, released from icy grains in the coma, or produced by breakup far from the nucleus. Dust isn't filler. It's a dossier on the solids that once orbited another star. Grain colors, redder or neutral, polarization, how scattered light is oriented, and thermal emission in the mid-infrared constrained size distributions, porosity and composition, silicates, organics, sulfides, maybe even salt. Look for the 10-micron silicate feature to weigh crystalline versus amorphous content. Crystals might whisper of thermal processing in the source disk before ejection. Some comets display a sodium tail, a faint needle-like extension from resonant scattering by neutral sodium atoms, an exquisitely sensitive tracer of certain minerals or sputtering processes. If the dust-to-gas ratio runs high, you're seeing a crustier, perhaps devolatilized surface. If it's low, fresher, fluffier stuff dominates. Either way, grains are time capsules with good hair. Observers often compress dust vigor into AFRA, pronounced AFRO, a handy pseudo-aperture measure combining albedo A, filling factor F, and projected radius ρ. AFRA's beauty is that it remains roughly constant with aperture for a steady-state coma, letting you compare activity across nights and comets without pulling your hair out. Gas production rates, on the other hand, fall out of fluorescence efficiencies, how brightly a molecule glows per unit sunlight, which depend on heliocentric distance and velocity. Put both together, and you get the dust-to-gas ratio, an index card that says crusty and dusty, or steamier than a sauna. All this anatomy also diagnoses health. Outbursts, sudden brightening by orders of magnitude, can indicate caverns of pressurized gas breaking through. Phase transitions, like amorphous to crystalline ice releasing trapped volatiles, or structural collapse. Fragmentation leaves secondary comae and mini-tails. Torque from asymmetric jets can spin the nucleus up or down, occasionally past its structural limits. Monitoring the coma's shape in high resolution can reveal collimated jets, fans, and spirals, geometric autographs of active vents and rotation poles. In short, the coma is not static fluff. It's a dynamic ECG of the nucleus. For an interstellar visitor, this dissection is gold. The mix of volatiles at large distances tests whether exotic ices survived its ejection and long cruise. The dust mineralogy probes formation temperatures and processing in a foreign protoplanetary disk. If the eye entails behavior systematically deviates from expectations, that might flag unusual parent molecules or grain charging properties. None of this needs an alien engineering explanation. The natural story is already thrilling, but if something refuses to fit the periodic table of cometary behaviors, say persistently unnatural polarization angles or emission features that don't map to known molecules, then eyebrows may upgrade to full committee meetings. Next, we'll swap microscopes for sniffers. How spectral fingerprints let us read the chemistry line by line, and what deviations would actually count as weird in a way your thesis advisor can't ignore. Spectroscopy, licking a lollipop with your eyes and calling it chemistry. When sunlight or starlight interacts with gas and dust around a visiting object, atoms and molecules absorb and re-emit light at razor-specific wavelengths, barcodes etched by quantum rules that refuse to improvise. Spread that light through a prism or grating, measure the intensity versus wavelength, and suddenly a bland fuzzy coma turns into a chatty ledger. CN whispers here, C2 hums there, CO pings in the infrared, and H2O clears its throat, mostly in bands your retina never sees. Start with the celebrity suspects. CN cyanogen radical is a mainstay in optical spectra, around 388-3090 nA. It's usually a daughter product, photochemistry breaking down nitrile-bearing parents, yet it provides a crisp, strong band that says organics on aisle 3. C2, the swan bands in the green, paints Come with a forest glow that has nothing to do with chlorophyll and everything to do with excited carbon dimers. These are not necessarily the dominant bulk molecules, but they're bright, tractable, and let you clock relative abundances across nights. If CN-C2 ratios skew wildly high or low compared to solar system comets, ears perk, different parent inventories or processing histories may be at work. Water, H2O, is the main engine for many comets closer to the Sun, but it's sneaky optically. Its strongest features live in the near IR. In the visible, you often infer indirectly via OH at UM308 Nalthamate, a photodissociation daughter, or you use space-based UV/IR assets when the atmosphere blocks your view. CO2 likewise sings most clearly in the infrared, while CO flaunts rotational transitions in the millimeter, sap-millimeter, and vibrational lines in the IR. That's why a proper chemistry workup looks like a band on tour. Optical spectrographs for CN-C2, C3, infrared instruments for H2O, CO2, radio receivers for COHCN, CH3OH, and friends. Each window sees different soloists. Together, you get the ensemble. Temperature rides along encoded in line shapes and relative level populations. In low-density cometary communal, molecules get excited by sunlight, fluorescence, rather than by cozy collisions. The resulting line ratios trace an effective rotational temperature that, while not a room thermostat, still tells you about the balance between radiation pumping, spontaneous emission, and redistribution processes. In the radio, the rotational ladder of CO or methanol acts like a tiny thermometer. Populate higher J lines, and you're looking at warmer or more pumped gas. Zoom in further, and the line widths betray expansion speeds. Broader lines can mean faster outflow or unresolved blends, and careful modeling separates the two. Spectra, in other words, are gossip columns that also quote their sources. Dust doesn't stay silent. Thermal IR spectra reveal silicate features near 10 and 18 microns, letting you weigh crystalline versus amorphous grains. Crystalline forsterite, or enstatite, implies heating and annealing back in the source disk before the object was ejected, a breadcrumb about its birth environment. Polarization-dependent scattering, technically not spectral, but often measured alongside, constrains porosity and size distributions. Combine that with color slopes, and you're sketching the grain family portrait. Fluffy aggregates, compact pebbles, organics-rich coatings, the works. Then there's isotopes, the accent marks of chemistry. Ratios like DH in water, 1 to 3 C through 1 quade C in carbon species, or 15N, CN, carry memory of temperatures and fractionation processes at formation. In our solar system, comets show a range of DH values, sometimes higher than Earth's oceans, sometimes intriguingly close. An interstellar object with a drastically off-book DH, say an order of magnitude away from common comet values, would hint at either much colder birth conditions or different fractionation routes. Likewise, a 115N enrichment beyond solar system norms would flag unusual nitrogen chemistry in its natal cloud or disk. Measuring these is hard. Lines get faint and tangled, but the payoff is huge. Isotopes are the chemical handwriting analysis that resists forgery. How do we decide something is weird rather than just individual? Step 1. Build context across heliocentric distance. CO2-H2O production ratios evolve with sunlight. Compare apples to apples by correcting for distance and activity level. Step 2. Watch time behavior. If a species spikes diurnal with rotation, the outgassing could be vent-localized. If it rises smoothly with raw moon-soaked heating, you're probably seeing global sublimation. Step 3. Compare to families. Solar system comets cluster into patterns. Typical, carbon chain depleted, rich in CO, and so on. A spectrum that parks outside all known neighborhoods, across multiple nights and instruments, is genuinely interesting. One loud line on one noisy night, that's not a plot twist. That's a coffee spill. Another red flag, forbidden lines or bands at wavelengths not matching any known cometary species, persisting after you rule out air glow, instrumental ghosts, and telluric contamination. If you required implausible excitation mechanisms to explain them, skepticism grows, but so does curiosity. Similarly, a polarization spectrum with angles or wavelength dependencies out of family might indicate exotic grain shapes or compositions. Note, exotic is not code for alien alloy. Nature can be plenty creative using only the periodic table and a large canvas of temperatures and pressures. Velocity-resolved spectra add a final layer, map a line across the coma, and you can tomograph the outflow. Blue shift on the sunward side, red shift anti-sunward, asymmetries where jets point toward or away. These kinematic fingerprints tie chemistry to geography on the nucleus. A CO jet peaking at dawn longitudes? That's a volatile pocket near a morning terminator. A distributed source of CN with a wide radial profile? Perhaps grains release nitriles as they crumble far from the surface. When chemistry maps onto a plausible physical story, confidence rises that you're seeing geology and sunlight, not mystery engines. Put it together and a clean verdict emerges. Spectra are both dictionary and diary. They translate unknown light into named molecules, and they recount how those molecules live, move, and change through a solar flyby. Weird, in a publishable sense, means stable, multi-wavelength departures from the cometary canon, corroborated by instrument-independent measurements and consistent with physics. If 3IATLAS checks those boxes, we won't need punchlines. The lines themselves will do the punching. Next, we trade wavelengths for motion. Can tiny non-gravitational nudges masquerade as propulsion? And how do we disentangle natural outgassing from a hypothetical low-thrust drive without jumping to sci-fi conclusions? Extraordinary claims need extraordinary receipts, preferably laminated. Before we go receipt hunting, we need an operational definition of probe. For our purposes, a probe is an artifact whose behavior or physical properties require intentional design by a technological agent, not just the blind, but creative chaos of astrophysics. Notice the verbs require, not merely permit. The standard isn't could be artificial if you squint, but natural explanations fail under quantitative tests, and a design hypothesis makes specific, testable predictions. So what would move the needle from eyebrow raise to call a colloquium? Start with dynamics. Non-gravitational acceleration is normal for comets. Outgassing acts like a messy thruster. A probe claim needs thrust that refuses to look cometary after modeling. That means, 1, the force vector doesn't track the sunlit surface where sublimation should peak. 2, the magnitude doesn't follow the expected heating law with heliocentric distance. And 3, the torque on the rotation state doesn't match what gas jets would do. If the object's spin remains unnaturally stable despite measurable accelerations, you're looking at controlled attitude rather than random venting. Bonus suspicion points if we see brief, step-like dial Vs, tiny course corrections, timed in ways that correlate with geometry, e.g., Earth line of sight, rather than sunlight. Natural comets don't schedule their burps. Now to signals. The cleanest techno-signature is a coherent beacon, narrowband radio, or a monochromatic laser flash. Narrowband means an emission line far slimmer than thermal or maser processes would produce, drifting in frequency precisely as if Doppler corrected for relative motion. A design signal will likely show structure, repetition at prime intervals, binary framing, polarization purity that stays locked over time, or deliberate on-off gating synchronized to celestial cues. The test here isn't philosophical, it's engineering. Does the signal occupy a bandwidth absurdly small for natural sources at the observed brightness? Does it persist across instruments and sites after we've slain the usual dragons, terrestrial interference, satellites, reflections, and instrumental ghosts? And does it stop when the target sets and reappear when it rises, like a lighthouse tied to the object's sky position, rather than our local wiring? If yes, that's not a lollipop, that's a label. Engineered materials provide another lane for evidence, even at a distance. Reflectance spectra of natural rocks and ices have recognizable broad features. Refined alloys or layered dielectrics can show unnaturally sharp edges. Flat spectral albiades across wide bands, or Fresnel-like polarization curves consistent with smooth, planar surfaces. Repeating, specular glints with identical timing across rotations, like a mirror flashing, argue for flat facets aligned to a stable body frame. In thermal infrared, an ultra-low emissivity surface could betray a coating optimized to dump or retain heat in ways geology wouldn't choose. Radar cross-section is yet another yardstick. An object that returns a radar echo orders of magnitude brighter than its size and roughness predict, especially with polarization flips characteristic of smooth plates, nudges the dial toward manufactured. None of these single observations closes the case. Together, they start to rhyme. Light curves can carry fingerprints of design too. Natural rotators tumble, precess, and evolve as jets torque them. Damping takes time. A body that locks into a long-lived, finely tuned rotation state, with a stable pole pointing at dynamically useful targets. The sun for power, Earth for comms, perihelion for thermal management, smells like guidance. If brightness modulations show sharp, regular eclipses, as if from periodic occulting structures, think radiator fins or booms, you've moved beyond potato with patches territory. And if the effective area-to-mass ratio inferred from dynamics is so high that only an ultra-thin sheet fits, plus the acceleration scales with 1R core trade, like radiation pressure, and changes with attitude, you've sketched a solar sail. Nature can make flakes. It seldom makes sails with attitude control. Let's talk falsifiability, because laminated receipts come with barcodes. A responsible probe hypothesis must issue predictions in advance. For dynamics, at R is 0.8 AU, the transverse acceleration will deviate from a water-ice sublimation law by XSS, and the spin phase will remain constant to within Y degrees over Z days. For signals, If the beacon is real, a narrow line at f0 with drift .f matching the barycentric correction will recur every t minutes. For materials, polarization at phase angle alpha will follow the curve of a smooth dielectric with refractive index n, not the Umov law typical of regolith. Write it down, then check. If the data refuse to comply, the hypothesis pays the bill, and we walk it back without drama. Science likes bold, it loves accountable. A parallel requirement is redundancy. Any claimed anomaly must be observed with independent telescopes, instruments, and analysis pipelines. For radio searches, that means on-off source nodding, multiple backends, and geographically separated sites to kill local interference. For optical flashes, it means coincident detections within light time windows and with time-stamped GPS-disciplined clocks. For dynamics, release the astrometry and force models allow blind refits and confirm that occult systematics like trailing losses or centroid biases aren't sneaking in as mystery thrust. If an effect vanishes when a different reduction code is used, congratulations, you discovered a pipeline, not a probe. What about dust and samples? If we capture grains from the tail, engineered materials would shout from the Petri dish, phases that don't occur in equilibrium geology, ultra-pure alloys with impurity levels too low for meteor processes, precisely layered films with micron-scale periodicity, or isotopic ratios that imply industrial separation rather than nebular fractionation. The bar is high because nature is clever. We need signatures that aren't just rare, but require intention. If you claim screws, you'd better show threads. One cautionary flag, pareidolia. Humans are factory installed to find patterns in clouds and static. That's why we front-load tests aimed at known natural mimics, outgassing jets, spinning shards, plasma effects, instrumental crosstalk, before writing designed on the whiteboard. And we keep Bayesian priors honest. The prior probability of stumbling on a probe is low, so the likelihood ratio has to be crushingly in favor of design, not cute headline, high math class high. Finally, ethics and protocol. Even if evidence mounts, we don't ping it with high-power radar or lasers without a debate. Planetary protection has a cousin called interstellar etiquette. First, do no harm. Second, don't reveal your address by accident. And third, publish openly so the conclusion, whatever it is, belongs to everyone. If the receipts exist, they'll survive sunlight, figuratively and literally. Next, we'll turn the spotlight on one sticky receipt in particular: non-gravitational accelerations. How to separate honest comet breath from engineered thrust without confusing steam for steering. Comets burp, probes steer. Our job is figuring out who had the lunch. The giveaway lives in the tiny persistent accelerations that nudge a trajectory away from the clean curve gravity. Alone would draw. Those nudges can come from sublimating gas jets, sunlight pushing on a feather-light fragment, or if you're feeling spicy, low-thrust propulsion and sails. The trick is not to romanticize the spreadsheet. We model the force, test its timing and direction, and see whether nature or engineering fits the bill with fewer excuses. First, the comet playbook. When ices sublimate, escaping molecules carry momentum. If vents are unevenly distributed, the nucleus gets a recoil kick. Astronomers fit this with simple three-component accelerations: radial away from the sun, transverse along the orbit, and normal out of the orbital plane, whose magnitudes scale with a heating law GR. For water ice, GR rises steeply as the object approaches the sun and collapses after it recedes. CO and CO2 activate farther out and decline more gently. Real nuclei spin, so sunlit vents switch on and off over a rotation, adding a diurnal rhythm and a thermal lag peak thrust hours after local noon. Jets also torque the body, changing its spin rate and sometimes its pole direction. Translation: comet thrust has a signature cocktail: heliocentric distance dependence, day-night breathing, and measurable spin evolution. Now the engineered options: low thrust propulsion, propulsion, Indron engines, cold gas jets, trickle-burn chemical systems, produces acceleration that can be held in a fixed direction for hours to days, then turned off in discrete steps. If attitude control is good, the spin state will look unnaturally stable, little to no drift in period or pole, despite sustained acceleration. Solar sails are a special case. The acceleration scales, ha1 r², like sunlight, depends on the projected area toward the sun, and flips or modulates when the sail changes attitude. If you can infer area to mass ratio from the dynamics, and it's orders of magnitude too high for a rubble pile, but perfect for a thin film, you've wandered into bring the whiteboard territory. Magnitude matters. Typical cometary non-gravitational accelerations sit roughly in the 10 Nemesis 10 Nemesis band near perihelion, fading rapidly with distance. You can get similar numbers from radiation pressure if the object's area to mass ratio is huge, as for dust scale shards or ultra-thin sheets. But shards also betray themselves photometrically. Fast fading, color changes, erratic light curves, and dust-like fragments don't maintain coherent spin for long. A steady, months-long acceleration with a tidy 1r² law and no gas detected at sensitive limits whispers large cross-section, tiny mass. Nature can chip off flakes. It struggles to make meter-class mylar. Direction is the lie detector. Sublimation thrust roughly aligns with the surface normal of active regions and, averaged over rotation, points somewhat sunward with a transverse bias set by vent geography. It does not lock to inertial space or to Earth's line of sight. Low-thrust engines can do both. Hold thrust in a chosen inertial direction, precess it deliberately, or pulse burns when geometry is advantageous, e.g., maximize plane change near nodes. Step-like residuals in the orbit fit. Little dial V increments at times, uncorrelated with solar heating, are classic fingerprints of burns, not boiling ice. Torque is the chaperone. Gas jets almost never give free acceleration without also twisting the nucleus. Watch the light curve. If the rotation period walks by minutes, or the phase drifts in a way consistent with asymmetric venting, you're smelling steam. If the body accelerates non-gravitationally, yet its spin period and poles stay rock solid for weeks, that's attitude control, either via propulsion or by the passive stability of a flat sail held in a fixed orientation. In practice, we build a coupled model, fit the trajectory and the spin evolution together. If a comet jet model needs contortions, implausibly placed vents, unphysical thermal lags, while a constant thrust or sail model nails both orbit and light curve with fewer knobs, Occam starts clearing his throat. Spectral and imaging forensics add muscle. Gas-rich thrust should come with evidence, CNOH in the UV optical, H2O CO2 bands in the IR, COHCN lines in the radio, enhanced polarization from dust, and visible jets or fans in high-resolution images. A sail or thruster stays shy. No gas lines, no dust coma growth, key to heating, perhaps even specular glints that repeat with rotation if flat facets exist. Ion engines could in principle leave a faint emission trail, but at interplanetary distances and low mass flow, it's vanishingly hard to catch. Their calling card is dynamical cleanliness, not neon lights. There's also timing psychology. Comets peak after perihelion, thanks to thermal inertia. Sails and engines don't care about seasons. They follow geometry or mission goals, plot acceleration versus true anomaly. If the curve lags sunlight systematically, you're baking ice. If it keys to orbital landmarks, ascending node, closest Earth approach, or toggles crisply on calendar boundaries, you're scheduling, not sublimating. Information theory helps keep us honest. Competing models can be compared with AICBC, penalize extra parameters, reward explanatory power. A comet jet model usually needs a handful of coefficients, 3 force components, plus a GR choice, and maybe a lag, A thrust model might need thrust magnitude, direction, and duty cycle. A sail model needs area to mass and attitude law. If the engineering model wins decisively, and the null tests independent astrometry, alternative reductions, barycentric versus heliocentric propagation, give the same answer, that's a result, not a vibe. Don't forget small imposters, radiation pressure-dominated chips, masquerading as a craft. Their acceleration also tracks 1R quadri, and they lack gas. The tell is physical, infer size from brightness and albedo, estimate mass from plausible densities, and check whether the required area-to-mass ratio demands thicknesses of microns over meters. If your best-fit object would blow apart under modest spin or micrometeoroid hits, it's likely a crumb, not a chassis. Occultations, thermal IR, or radar, if feasible. Tighten those size-mass bounds and collapse the ambiguity. Finally, embrace ensembles. Fit the orbit with multiple independent pipelines, split the astrometry by observatory and by trailing rate to catch centroid biases, test water ice versus CO-driven GR, allow for diurnal terms, then try constant thrust and sail laws. If only one family of models survives cross-validation and agrees with the spin and the spectra, you've earned a headline. If several fit, you've earned another night on the telescope. Science isn't allergic to romance, it's just married to calibration. Next up, we'll mine the flicker itself, how radar echoes, light curve shapes, and spin states can betray geometry from lumpy potatoes to improbable toasters, and why shape matters when you're hunting sails, booms, or anything built rather than baked. If it's shaped like a toaster and acts like a toaster, we still need better data. Long-distance shape sleuthing is the art of extracting geometry from flicker, echo, and color when the object itself is a sub-pixel smudge. 3 tools dominate: radar, light curves, and photometric albedo, each powerful, each loaded with caveats big enough to park a telescope dome in. Start with radar, the gold standard when you can swing it. A planetary radar dish, think Arecibo when we had it, or Goldstone, pings the target with a high-power signal and listens for the faint echo. The time delay gives distance with kilometer precision. The Doppler, spread across frequencies, maps rotation. Different parts of a spinning body shift the echo up or down in frequency. Combine delay range and Doppler velocity to paint range Doppler images, not photographs, but 2D projections that reveal silhouettes, large facets, and sometimes bolder scale topography. The catch? Radar is merciless about brightness falling off with distance, roughly like 1R4, when you consider both the outgoing and returning path. Interstellar visitors are typically too far and too faint for anything but the most heroic attempts, and even then, you get low signal-to-noise smudges that whisper rather than sing. If you do snag an echo, polarization ratios can flag surface smoothness, rough regolith depolarizes, while mirror-like planes can flip or preserve polarization in telltale ways. But absence of a strong echo is not proof of smoothness or small size. It might just be proof that physics hates inverse fourth law budgets. So we lean heavily on light curves, time series of brightness, as the object rotates. Imagine a lumpy, elongated nucleus turning in sunlight. Its projected area toward us changes with phase, modulating the flux. A high-amplitude, periodic curve suggests an elongated shape. A low amplitude hints at something more spheroidal, or at a viewing geometry, looking down a pole. If the period is clean and stable, you get a principal axis rotator, spinning like a tidy top. If the curve is messy, multiple frequencies, beating patterns, or drifting phases, you've likely got a non-principal axis state, a tumbler, where the spin vector precesses and the body wobbles. Tumbling is common after torques from outgassing or gentle impacts. Damping back to a single axis spin can take thousands of years for small, rigid bodies. From the amplitude dm, you can infer a lower limit on the axis ratio, AB simply 10 by 0.4. ADM of 1 magnitude implies AB simply 2.5. Think cigar or pancake, not potato. But light curves lie if you don't interrogate them. Albedo variegation, bright and dark patches, can fake shape effects, turning a mottled sphere into a shape imposter. Phase angle, sun-object observer geometry, also matters. At high phase angles, shadows on rough terrain deepen, inflating amplitude. At low angles, everything looks flatter. To reduce the illusions, observers chase multi-filter light curves across a range of phase angles and tie them to color. If amplitude persists identically in filters, shape dominates. If it varies with wavelength, albedo patterns are in on the prank. Sparse sampling can also alias the true period, half-period solutions masquerade as truth. If you only catch every other peak, the cure is obsessive cadence and independent teams. The cosmos rewards stubbornness. Albedo, the fraction of sunlight reflected, adds another constraint. Measure brightness, estimate size, and you've implicitly assumed a reflectivity. Flip the equation. With a thermal infrared detection, you can solve for both diameter and albedo. Using energy balance, more thermal flux for a given optical brightness implies low albedo and larger size. Without thermal data, size albedo degeneracy is a bully. The same brightness could be a small, shiny chip or a big, dark lump. Interstellar visitors at long range often lack thermal detections deep enough to break the tie, so we lean on population priors, but we keep the error bars honest. If dynamics suggest an enormous area-to-mass ratio, a high albedo thin sheet becomes plausible, but we don't let plausibility dress up as proof. Why we care about shape goes beyond aesthetics. A sail or structured artifact would imprint geometry on both the light curve and the dynamics. Flat facets produce specular glints, brief, sharp brightenings when the facet angles the sun to observer path just right. Repeating glints at a fixed rotation phase argue for persistent planar elements, not just random boulders. An ultra-high light curve amplitude with stable phase over long spans suggests both elongation and rotational discipline, odd for a vent-torqued comet, but natural for an object with attitude control or strong internal cohesion. Meanwhile, a tumbling state with erratic amplitude growth points to recent torques, outgassing, fragmentation that sails don't enjoy. Add polarization. Smooth plates can generate high, angle-dependent polarization, not typical of dusty comets or rough regolith. Each clue is small. Together, they start forming a silhouette. We should also mention the pancake versus cigar trap. A rotating disc seen edge-on can mimic a thin rod in light curves. Both deliver large amplitudes. Disambiguating requires geometry. How does amplitude change as the phase angle evolves? And do we witness mutual events, eclipses or self-shadowing, consistent with a very thin thickness? Thermal inertia helps too. A wafer cools and heats rapidly, shifting thermal light curves relative to optical ones. A bulky rod lags. Without thermal data, we collect hints, phase angle dependence, glint frequency, and whether the rotation period drifts in a way consistent with radiation torques, Y or P. If Yorp seems to be driving the spin quickly in a direction that matches a high area-to-mass geometry, a thin shape becomes likelier. Limitations deserve boldface. Distant photometry is haunted by systematics. Background stars contaminate apertures, trailing smears, centroids, and flux. Changing seeing moves light between the aperture and the sky. Annulus. Professional pipelines fight these with PSF fitting, non-sidereal tracking, and carefully selected reference stars, but residuals remain, especially near the detection limit. That's why we prize convergent evidence, period from one observatory, amplitude from another, phase behavior checked a month later, and if we're fortunate, even a lucky occultation of a background star to pin down silhouette size directly. One clean star blink can slash size uncertainties and shut down a whole zoo of phantoms. Bottom line, Shape diagnosis at astronomical distances is a courtroom built on circumstantial evidence, compelling when consistent, fragile when isolated. Radar is the surprise eyewitness. Light curves are the chorus of neighbors. Albedo is the blurry security cam. If they all hum the same tune, elongated body, stable rotation, specular hints, odd polarization, then toaster graduates from joke to model. If not, we keep the label maker in the drawer. Next, we pivot from geometry to timing. Perihelion as a stress test, what a solar flyby does to ices, cracks, and chemistry, and how a close pass can turn a quiet speck into a laboratory experiment with the sun as the Bunsen burner. Perihelion, the cosmic equivalent of putting it under a heat lamp and seeing what melts first. When an interstellar visitor swings past the sun, we get a controlled torture test, courtesy of stellar physics. No grant proposals, no lab ovens, just inverse square law and a ticking clock. What we watch during this flyby isn't merely brightness, it's a cascade of thermal, mechanical, and chemical reactions that reveal what the object is made of and how it's put together. Start with the thermostat. To first order, a sunlit patch approaches an equilibrium temperature set by absorbed sunlight, balanced by re-radiated heat and sublimation losses. The thermal skin depth, how far the daily heat wave penetrates, may be centimeters to decimeters, while the seasonal wave for a tilted body on an eccentric path reaches deeper. Layers beyond the skin remain cryogenic, while the surface cycles through bake, crackle, vent, result, a crust that expands and contracts while the interior shrugs, storing stress like a spring. Stress means fractures. Weak cometary materials have tensile strengths measured in tens to hundreds of pascals. Think snowdrift, not granite countertop. As temperatures rise, trapped volatiles pressurize pockets below dust mantles. When the overburden fails, you get jets. When it really fails, you get slabs exfoliating, cliffs collapsing, or the whole nucleus shedding fragments. Near perihelion, even small changes in rotation can tip a precarious balance, spin up from asymmetric jets, or radiation torques nudges centrifugal forces past cohesion, and suddenly your single object is a family reunion with debris. Not all breakups are spectacular. Microfragmentation can quietly boost the dust cross-section and mimic a smooth brightness surge. Chemistry spikes ride on this thermal roller coaster. As fresh fractures expose new ice, production rates for different molecules don't just increase, they change character. Water takes over closer in, but more volatile species like CO and CO2 can peak earlier or persist longer, sculpting a multi-peaked activity curve. Photochemistry in the expanding coma accelerates, daughter species blossom, forbidden oxygen lines brighten, and the iron tail becomes a seismograph for space weather. Perihelion is also prime time for sodium tails. Narrow, needle-like features from resonant scattering by neutral NA, liberated from grains, subtle but exquisitely sensitive to heat-driven release. Each species has a preferred alarm temperature, so the timing of their peaks is a fingerprint of stratigraphy rather than a single comet on-off switch. Navigation is a thriller. Ephemeris uncertainty inflates your where-to-point ellipse right when you least want ambiguity. The cure is optical nav, with synthetic tracking and a search raster that can sweep the uncertainty box quickly, guided by onboard star catalogs and Kalman filters that ingest every new centroid to collapse the box in real time. A flash LiDAR, or star tracker-assisted autofocus tightens final approach, while a preloaded playbook handles contingencies. If SNR threshold, widen exposure. If streaking exceeds limit, drop to shorter integrations. If target lost, execute expanding lawnmower. You don't phone home for permission, you do and report. Power and comms ride the same seesaw. Near the sun, solar arrays are happy campers. Far out, they starve. A rapid intercept typically lives within a few AU, so solar is viable with careful thermal design. For downlink, Ka-band is standard, but consider an optical comms add-on. Laser downlink gives you high data volumes from a small aperture if weather cooperates at your ground station. Worst case, you carry a deep buffer and dribble the haul over weeks. The absolute non-negotiable is time tagging. Nanosecond class clocks anchor light curves and spectra to geometry. Without them, a lot of flyby data becomes pretty but toothless. Money and schedule realities shape the menu. A shelf mission, hardware built to 90% and stored, burns budget annually but shaves months off response. A kit of parts approach, standard bus plus swappable plates for instruments and antennas, lowers per mission integration time. Regulatory hurdles, frequency licenses, range safety, planetary protection paperwork are the sneaky killers of rapid. Pre-clear as much as possible, including contingency approvals for launch windows outside the usual campaign seasons. Finally, risk posture. With a single pass at ludicrous speed, your philosophy is graceful degradation. Every instrument can deliver standalone wins. Loss of one doesn't zero the mission. Redundant star trackers, cross-strapped power, and dumb simple safe modes that still collect something during comm dropouts can upgrade a partial to a publishable success. And because we may want not to annoy hypothetical neighbors, we keep active illumination, radar, lasers on a leash, pre-deciding what's acceptable long before adrenaline says, try it. The playbook, then, pre-position small, adaptable interceptors, cultivate propulsion options from kicks to sails, keep a perihelion hot rod on the whiteboard, and rehearse autonomy like a dance routine. When the next interstellar spec appears, you don't negotiate with the clock, you launch, you sprint, and you make the one shot count. Next, we'll zoom down to the grain scale, how dust capture and microanalysis can turn a flyby's tiniest souvenirs into a chemistry lesson from another star, CSI Comet, because every grain is a tiny alibi. When an interstellar visitor sheds dust, it's not littering, it's confessing. Those specs, micron to millimeter, encode formation temperatures, radiation histories, and sometimes manufacturing secrets, if any exist. Unlike distant light curves and spectra, dust lets you poke the evidence, weigh it, heat it, and ask rude questions under a microscope. Step 1 is catching the stuff without turning it into plasma confetti. Relative speeds in a flyby can be 5 to 70 kilometers s, and at those velocities, a naked collector plate is a gilt shredder. That's why aerogel, an ultra-porous, low-density silica foam, earns hero status. A grain burrows a tapered track, decelerating gently enough to survive as an intact core, with a smeared carrot of ablated material behind it. Track geometry itself is a clue. Steeper, longer tracks flag higher impact energy. Branching or splashes suggest fragile aggregates that broke apart in flight. If we can fly multiple tiles at different densities, we tune the capture to both pebbles and powder, minimizing thermal alteration while still stopping the projectiles before they redecorate the avionics. Contamination control is the difference between alien dust and workbench dandruff. Collectors must be baked to drive off volatiles, assembled in clean rooms, and sealed with witness plates, blank substrates that ride along to record background contamination. After recovery, the chain of custody looks like a crime lab. Nitrogen cabinets, non-metallic tools, archival labels, and QR-tracked subsamples. Every solvent rinse, every sputter coat, every microtome slice gets logged so downstream analysts can separate the comet story from our fingerprints. Once in the lab, the fun begins. Optical and electron microscopy map structure, from submillimeter down to nanometer scales, fluffy aggregates of submicron grains, compact chondrule-like fragments, glassy spherules that hint at flash heating, layered laminates where none should be, energy dispersive X-ray spectroscopy, EDS, and electron probe microanalysis, EPMA, sketch elemental budgets, Mg, Fa silicates, sulfides, metals, organics, transmission electron microscopy, peers into lattice order, crystalline forsterite versus amorphous silicate, annealed rims, radiation-damaged tracks. A single grain can carry zones that formed under wildly different conditions, like finding beach sand welded to volcanic glass with a dusting of soot. That juxtaposition is a postcard from a turbulent protoplanetary disk. Mineralogy anchors origin stories. Abundant crystalline silicates imply thermal processing above E100K, while amorphous matrices whisper cold and fast. High-temperature calcium aluminum-rich inclusions, CAI-like bits, would be startling in an interstellar sample. But even partial analogues, exotic refractory assemblages, would raise eyebrows. Sulfide species, troilite, pentlandite, trace sulfur chemistry and redox states. Metal grains, Fe9, with specific Co-P, speak to reducing environments and cooling rates. Organics matter too. Aliphatic versus aromatic signatures in micro-FTIR and Raman spectra, nitrogen content, and functional groups tell us whether organics were baked, irradiated, or assembled gently in ices. If we catch fragile, highly porous aggregates with ultra-low density, we're likely sampling primordial fluff rather than processed rock, evidence that the parent system ejected material early, before heavy collisional gardening. Isotopes are the lie detector that doesn't blink. DH in water and organics, 115s N in nitriles, 1-thokib C, 1,1,2D C in carbon phases, and the oxygen trio, 1-Phasian thermometers and provenance tags. Secondary ion mass spectrometry, SIMS, LanoSIMS, can raster across submicron domains, revealing isotopic hotspots, presolar grains with wild anomalies, for instance, that predate any star system chemistry. If an interstellar dust grain shows isotopic ratios markedly outside the spread known from solar system comets, that's strong evidence of non-local, i.e., born in a different nebulous soup. Conversely, a familiar isotopic palette would argue that disk physics rhymes across stars, useful in its own right. Noble gases add another layer. Trapped neon, R, crew, see in glassy inclusions or bubble vesicles, act like time capsules. Their isotopic fingerprints can indicate irradiation histories and closure temperatures. Implanted solar wind-like signatures would suggest long surface exposure after ejection. Exotic noble gas patterns might hint at different stellar winds or supernova contributions near the birth cloud. Because noble gases don't react, they remember even when minerals forget. What would qualify as non-natural? The bar is high. Start with alloy chemistry. Ultra-pure aluminum with ppm-level impurities. Unlikely from cosmochemical processes. Fe9 alloys with phase diagrams, attainable only under controlled cooling. Or systematic doping, e.g. specific rare earth distributions, inconsistent with nebular condensation. Microstructure can betray intent. Periodic multi-layer stacks with submicron regularity, a Bragg reflector, fibers woven into a composite, or foamed metal with pore sizes tuned to exact distributions. Polymers are even louder. Long-chain synthetics with repeating units not produced by abiotic pathways, or cross-linking patterns that scream factory, not photochemistry. Thin film interference fringes with uniform thickness over square millimeter patches would be hard to square with splat cooling or shock vanes. Any one of these would be spectacular. Multiple together would move non-natural from bar talk to peer review. But nature is clever. Shock metamorphism, lightning-like discharges, and impact plumes can produce glasses, laminations, and even periodic features that tempt us into overreading. That's why we ask for ensembles of evidence. Engineered-looking microstructure plus anomalous isotopes that hint at industrial separation. Alloy purity paired with trace element patterns that defy condensation sequences. Polymeric residues alongside inorganic scaffolds that fit no petrogenetic pathway. When lines of evidence converge, the mundane explanations run out of places to hide. What if we can't bring samples home? In situ microanalysis isn't powerless. Time-of-flight mass spectrometers can catch and vaporize dust on impact, reading elemental and molecular fragments. Laser-induced breakdown spectroscopy, LIBS, paints quick elemental barcodes. If a flyby can execute multiple passes through distinct parts of the tail, sunward jets versus anti-tail planes, we can map compositional heterogeneity, testing whether species cluster along structural axes, vents, or, in a wilder scenario, exhaust patterns. Even impact plume spectra from a sacrificial penetrator could reveal volatiles without intact capture, though that edges toward don't poke the mystery. Finally, statistics save us from single-grain mythology. We want distributions, grain sizes, porosities, DH ranges, crystalline fractions. Outliers are interesting. Populations are conclusive. If 80% of grains look solar system familiar and 20% carry unmistakably foreign isotopic accents, the story is mixed heritage or selective ejection. If 0.1% look engineered and the rest don't, we reach for contamination logs before we reach for headlines. Dust is humble, but it testifies under oath. Whether it says, "I condensed near a red dwarf snow line," or "I once was part of a radiator panel," the case will be built grain by grain, track by track, isotope by isotope. Next, we'll zoom out from microscopes to priors. How often weird should occur, and how to keep probabilities honest when rare events start tempting us toward narrative acrobatics. Low probability doesn't mean zero. Ask any lottery winner or hydrogen atom. When an interstellar visitor does something eyebrow-raising, the scientific impulse is to ask, how weird is weird? That's a statistics question long before it's a sci-fi headline. If we don't set the probabilistic stage, we'll mistake the universe's normal randomness for a conspiracy. Or worse, adjust our beliefs by vibes rather than numbers. Start with Bayesian priors, the seatbelts of inference. A prior encodes what we think before seeing the new data. Artificial probe has a low prior because we've never confirmed one. Natural comet behavior we don't fully understand has a high prior because nature is an overachiever with a long resume. A clean update uses Bayes' rule. Posterior, likelihood, tras, prior. The likelihood asks, if hypothesis H were true, how probable are these data? The prior asks, how plausible was H before we looked? If the data are surprising under the natural hypothesis and expected under the artificial one, the odds can swing, but the swing must overcome the prior. Extraordinary claims must earn enough likelihood to pay down the prior debt. Now, the trap called selection effects. We don't observe a random slice of reality. We observe what our instruments, schedules, and attention let through. Surveys are more likely to flag fast, bright, unusual things. So weird is overrepresented in the discovery catalog. That's discovery bias. Also, because dozens of teams poke at data, the most striking plots travel fastest, winner's curse, and their uncertainties are typically underestimated because the selection step is ignored. Proper inference conditions on the way a target was found. If you only look at comets that survived a weirdness filter, you must model that filter or overestimate how rare the surviving weirdness truly is. There's also the look elsewhere effect. If you test enough properties, colors, periods, polarization angles, acceleration components, emission lines, you'll find at least one that lands a few sigma from the mean just by chance. This isn't the cosmos winking, it's combinatorics. Correct by controlling the family-wise error, Bonferroni-type penalties, or, better, by doing Bayesian model comparison, where extra parameters are penalized automatically through the Occam factor. A model that fits because it's flexible doesn't get a parade, it gets a prior haircut. Speaking of model comparison, the right tool is the Bayes factor. How much more or less likely the data are under Model A than Model B? It's the evidential seesaw. Importantly, Bayes factors depend on how you define each model and its parameter ranges. If the engineered Sale model only fits when you assume an area-to-mass ratio within a tight sliver, the prior volume on that sliver is tiny. the model pays a penalty for being picky. Conversely, if a natural outgassing model requires implausible vent placements or thermal lags to work, it pays its own complexity tax. Numbers, not adjectives, decide who pays more. Another villain? P-packing by accident. If you tune data processing until an anomaly appears, choose a smoothing scale, pick nights, exclude bad frames, adjust background windows, you're doing multiple analyses and reporting the best-looking one. The cure is pre-registration. Specify analysis thresholds and stopping rules before opening the box. In practice, that means templates for photometry/atrometry reductions, predefined cuts for sky brightness and FWHM, and locked-in likelihoods for dynamical fits. Deviations from the plan must be declared and sensitivity tested. Stopping rules matter because we watched until we saw something odd. Biases odds. Sequential looks must be modeled with sequential statistics. In Bayesian terms, that's natural. Keep updating. In frequentist terms, use alpha spending or sequential tests so your false positive budget doesn't evaporate on the first curious bump. Calibration is the quiet cornerstone. Posterior predictive checks ask, if our chosen model is true, could it reproduce the distribution of residuals, not just the headline metric? Simulate fake datasets from the posterior, run the same pipeline, and see whether anomalies pop out as often as in reality. If simulated comets frequently yield mystery accelerations because of seeing dependent centroid shifts, your anomaly lives in the pipeline, not the sky. Population thinking beats single object mystique. Build hierarchical models where individual objects draw parameters, e.g., dust to gas ratio, non-gravitational force coefficients from population distributions. Then ask whether our current object is an outlier given that distribution. Outliers exist even in honest populations. They only become evidence against the population model if their tail probability, after all corrections, is implausibly small. If we've examined n visitors and you're shocked to find one in the 1% tail, remember, with n100, you expect a 1%er. Statistics is the friend who ruins magic tricks by explaining them and saves you from betting the house on them. Power analysis matters too. Before calling a non-detection constraining, compute the probability that your setup would have detected a genuine signal of reasonable strength. If your radio search had only a 20% chance to catch a narrowband beacon at a given flux, then we didn't hear anything. Barely moves the posterior. Conversely, a 99% power null result crushes the beacon hypothesis without drama. The same logic applies to spectral lines, polarization signatures, or glints. Don't forget prior sensitivity. Vary the priors within defensible ranges and report how the posterior shifts. If your conclusion flips when you nudge a prior on, say, sail thickness or vent latitude, you don't have a result. You have a hypothesis looking for data. Robust conclusions survive modest prior tweaks, like a well-built bridge survives a breeze. Lastly, publication bias. Null results rarely trend, but they are the scaffolding for real inference. A registry where teams log non-detections, failed follow-ups, and almost observables stops the literature from overcounting anomalies. Without the quiet data, the loud points look special by default. Put all of this together, and weird becomes a number, not a mood. Low prior, high Bayes factor, maybe we update. Low prior, modest Bayes factor. We admire the curiosity and keep observing. High prior, low Bayes factor. We shrug and tighten error bars. The universe throws dice. Our job is to know the rules of the game before we shout, loaded. Next, we'll step out of the spreadsheet and into the spotlight. How to communicate all this without either hyping ourselves into a corner or draining the wonder skepticism with a smile, and a plan for when headlines outrun histograms. Clickbait says, aliens now. Science says, let's calibrate first and panic later. When a new interstellar visitor lights up feeds, the pressure cooker isn't just in the comet's crust, it's in the attention economy. Headlines want a plot twist. Journals want a p-value. The public wants a story before sunset. Our job is to deliver wonder with seatbelts. Begin with the narrative spine. Questions first, claims later. Frame the discovery as a sequence of tests instead of a verdict. Here's what we know, what we're measuring next, and how each result will move the needle. Beats mystery object? Could be X, because it allows people to track progress like innings, not rumors. Curiosity doesn't die when you show the playbook. It grows when the audience can predict the next pitch. Next, practice disciplined vocabulary. Candidate, tentative, and consistent with are not weasel words. They're guardrails. Reserve evidence for until a result survives independent replication. Retire, never seen before, unless you've actually checked. Spoiler, someone has seen something like it at least once, usually in 1987, in an obscure proceedings volume with a teal cover. If you must use metaphors, pick ones that explain physics rather than inflate mystery. The ion tail snapped due to a solar wind shift carries more signal than the comet lost its mind. Visuals matter more than adjectives. A clean figure with time on the x-axis and a measurable quantity on the y-axis, annotated with instrument, uncertainty, and key events, disarms speculation. Put the raw points there, not just the smooth curve. If a journalist can screenshot your plot and tell the story, you've inoculated the discourse against wild takes. Bonus, release a tiny, well-documented data slice alongside timestamps, filters, exposure times, so interested amateurs can replicate a light curve instead of replicating your rumor. Establish a tiered communication cadence. Tier 1, rapid facts, discovery circumstances, basic orbit, brightness, in a short bulletin within hours. Tier 2, preliminary analyses, e.g., first color measurements, no gas upper limits, with clear caveats after cross-checks, ideally 24-48 hours later. Tier 3, deep dives, after internal review, and at least one external replication. Each tier answers specific questions and explicitly defers others. This pacing dials down the dopamine-fueled rumor spiral without freezing the conversation. Handle uncertainty like an adult. Quantify it. If the non-gravitational acceleration is 3.2 minus 0.8, say that not a tiny push. If you don't know the rotation period yet, state the aliasing culprits and the conditions that will break them. Explain what would falsify your favorite interpretation. Real skepticism is not a vibe, it's a to-do list with thresholds. Social media is both booster and blender. Use threads that start with the settled bits, then label speculative sections as such, literally with a heading like speculation, clearly labeled. Link to living documents, FAQs, observing plans, data repositories, so new readers don't parachute into page 7 of a conversation and mistake a conditional for a conclusion. Pin an updated summary. If a preliminary claim changes, quote tweet yourself with correction in the first word. The internet forgives honest updates. It punishes quiet edits. Press relations, make friends with your press office before the object appears. Draft template language when you're calm, not sleep-deprived, at 3 a.m. Include 3 components: a 1-sentence elevator pitch, a 150-word explainer for general audiences, and a 400-word technical note. For each likely observable, radio search, polarization, spectroscopy, pre-write, 2 outcomes, detection versus non-detection, with plain language implications. That way, when results arrive, you're swapping numbers, not writing epics. Avoid the embargo trap that turns nuance into a cliffhanger. Embargoes can coordinate coverage, but don't dangle breakthrough promises to manufacture drama. If a result is fragile, say so. If it's robust, the data will carry it without fireworks. And if an embargo slips because someone posted a teaser GIF of a mysterious spike, do the adult thing. Release the plot, the method, and the caveats immediately. Sunlight is as good for rumors as it is for comb pie. Invite scrutiny on purpose. Publish reduction code, or at least a minimal working example with fake data. Share calibration frames, or a handful of raw images so others can test for the usual gremlins, flat field issues, trailing losses, sky subtraction bias. When people can reproduce your pipeline, the conversation moves from, "Is this real?" to "What does it mean?" A far healthier place to be when the public is watching. Handle speculation with asymmetric rigor. If someone proposes an engineered sail, they should offer a quantitative fit, not a vibe. Ask for predictions. Okay, your model implies a 1 r² acceleration of magnitude A and a stable spin with phase phi. Shall we check next week? This turns what could become a narrative knife fight into a shared experiment. Don't dunk, document. If the prediction fails, log it in a visible claims and outcomes table. Keeping receipts isn't petty, it's pedagogy. Don't neglect the wonder. People aren't tuning in only for error bars. They're here because a rock from another star just strolled through the neighborhood. Use the poetry judiciously. A postcard from another planetary nursery. The sun acting as a natural spectrometer. A 1,000,000-kilometer windsock tracing invisible magnetism. Serve awe in measured doses so it highlights the arc of testing rather than replacing it. Finally, designed for endurance. The news cycle is a mayfly. The object's arc lasts months. Maintain a living FAQ. Update plots on schedule, even when the answer is no change. And celebrate null results that close doors gracefully. Curiosity doesn't need constant cliffhangers. It needs trust that each chapter leads somewhere, even if that somewhere is we learned how not to fool ourselves. Next, we zoom into the wholesome scenario. If 3IATLAS turns out to be entirely natural, why that's still a jackpot, and what such a verdict would teach us about other planetary nurseries across the galaxy. Thermal inertia, the material's reluctance to change temperature, adds personality. Low inertia surfaces respond instantly. Morning jets switch on like coffee makers. Sunset shuts them down. Higher inertia smears the response. Maximum outgassing lags local noon, and, on the orbit scale, often post-perihelion. That asymmetry, rising gently before perihelion, peaking after, tells you the heat wave needs time to percolate into volatile-rich layers. Watch the light curve and spectra across the arc, and you can back out both inertia and layering without ever touching the rock. It's armchair geology with a stellar spotlight. Mechanical feedback loops keep things lively. Jets don't just vent, they push. Near perihelion, production rates soar, and with them the recoil forces that adjust the spin period and precess the pole. Those changes, in turn, alter which vents are sunlit, reshaping the jet map on timescales of days. The system is self-editing. A vent that overperforms can torque the nucleus until it self-shadows, throttling itself. Meanwhile, gas drag lifts dust of all sizes. Micron grains paint the classic curved dust tail. Gravel and pebbles stay closer to the orbital plane, thickening a stubby fan. Ejector velocities increase with gas flux, so perihelion is when you're most likely to catch fast, collimated plumes and spirals that trace rotation poles, geometry scribbled in sunlight. The plasma ballet intensifies, too. Stronger UV flux and denser gas make ionization brisk. The ion tail couples harder to the solar wind's magnetic field. Coronal mass ejections sweeping past can trigger disconnection events, where the ion tail seems to snap and regrow. An unintentional magnetometer on a 1,000,000-kilometer stick. If we see repeated kinks or fast rotations in tail orientation that correlate with solar wind conditions rather than the object's own rotation, we're reading upstream space weather as much as local chemistry. Perihelion puts both on the same page. Observationally, this is the golden hour for contrasts. Narrowband filters tuned to specific molecules light up. Polarization curves steepen as fresh, fluffy aggregates dominate scattering. Thermal infrared brightens, letting us disentangle size and albedo. And if we're lucky, stellar occultations by the denser coma reveal density profiles in silhouette. Even non-detections are instructive. If deep searches still can't find gas when the heat lamp is on high, you can put quantitative limits on volatile inventories and surface permeability. Conversely, a sudden, brief surge, an outburst, lets you measure expansion speeds from line widths and follow a shell of gas as it dilutes, turning the coma into a time-of-flight experiment. The risks are part of the dataset. Fragmentation near perihelion can scatter the photometric signal across multiple pieces, scramble the rotation state, and reduce any hope of long baseline tracking. But the debris also offers forensic clues. Differing colors among fragments hint at heterogeneous layering, diverging non-gravitational accelerations, map area-to-mass ratios, fading rates expose which pieces are icy versus dusty. Think of it as a failed stress test that still returns a full report, just in confetti form. Bottom line, a solar flyby is a natural laboratory where temperature dials, mechanical stresses, and chemical pathways all swing into the measurable range at once. If the visitor is a conventional icy body, perihelion will read out its layering, strengths, and volatiles with ruthless clarity. If it's anything stranger, this is when the deviations will be largest and the excuses hardest to sustain. Next, we'll confront a different kind of limit: geometry. How the dance of sun, earth, and object can hide the best fireworks behind glare, horizon, or sheer bad timing. It's like the universe scheduled the concert for when your eyelids are the curtains. The most revealing moments in an interstellar visitor's life can unfold at solar elongations, so small that Earth-based observers are effectively staring into a floodlight. Geometry, not enthusiasm, decides what we get to see. Begin with elongation, the angle between the object and the sun on the sky. Most ground telescopes have a do-not-point cone around the sun. Point too close, and you roast sensors, or, at minimum, drown in scattered light. That means delicious phases of activity. Switch on, far from Earth. Peak out gassing near perihelion. Rapid evolution right after may occur, inside a forbidden zone. Even if an observatory does allow low elongation work, the sky background at twilight is a grainy mess. You're chasing a faint, moving pinprick through a field of skylight that refuses to sit still. Twilight isn't your only foe. Altitude is too. An object hugging the horizon forces you to peer through a thick slice of atmosphere. Extinction eats photons. Seeing smears detail and differential refraction displaces centroids in color-dependent ways that make precise astrometry pout. Low altitude also means trees, domes, and mountains join the conspiracy. The sky might technically be clear, but your target is playing peekaboo with a pine forest. Then comes the moon, astronomy's friendly neighbor who occasionally shines a flashlight in your eyes. A bright moon near your target sprays the detector with scattered light and ghosts, flattening the faint structures in a coma or tail you hope to measure. Observing plans juggle lunar phase like a wedding planner with too many cousins, push deep imaging to dark time, accept higher noise in bright time, or pivot to filters less sensitive to sky glow. If a critical event, an outburst, a fragmentation, lands smack on full moon, you can feel celestial scheduling laughing gently. Declination matters as much as elongation. A visitor swooping through far southern skies is visible only to southern observatories, and vice versa. Cross-hemisphere handoffs sound easy, but require coordination, weather luck, and identical calibrations if you want seamless light curves. Add Earth's own orbital motion, and your observing window can compress into short pre-dawn or post-sunset sprints. A few precious minutes nightly, where the object clears the glare, climbs above minimum altitude, and sets before you can finish your coffee. Miss 2 nights of that, and an entire segment of the evolution timeline is gone forever. Rate of motion is another geometric headache. Near Earth, apparent motion can spike to arc seconds per second, trail the target, and stars streak, track the stars, and the target smears. Either way, signal-to-noise melts. Non-sidereal tracking solves part of it, but exposure times still cap out before trailed smudges eat your contrast. Astrometry also gets cranky. When the point spread function stretches into a matchstick, The centroid shifts systematically, and orbit fits punish those biases. The fastest action can happen exactly when your cleanest measurements are hardest to obtain. Spacecraft don't escape geometry's rules, they just get different ones. Solar avoids exist for space observatories too. Thermal and power constraints define keep-out zones. Downlink windows, instrument duty cycles, and pointing priorities compete with your interstellar itch. Even if a spacecraft can look close to the Sun, spacecraft sun target angles determine stray light, scattered heat loads, and detector persistence. And then there's parallax. Different platforms see different sky paths. Coordinated observations can triangulate 3D positions fabulously, but only if clocks and pointing models are nailed with ruthless precision. Mission planners have a separate geometry-induced ULSA launch windows. To intercept or even perform a high-speed flyby, you need the right departure date, departure direction, and enough delta V to rotate the heliocentric velocity vector toward the target's plane. Plane changes are poison. A few degrees of inclination cost more propellant than your budget would like to admit. Miss a narrow window, and you often wait months while the synodic geometry realigns, by which time the target may be dim, distant, and as photogenic as a grain of pepper. People love to say, just launch, as if rockets were Uber. The ephemeris rolls its eyes. Even free assists come with strings. A gravity assist off Earth or Venus can bend your path toward the visitor, but only if the planets are in the right places at the right times. The same choreography that makes assists powerful also makes them rare. Add the need to avoid deep eclipses, harsh thermal environments, or communications blackouts, and your exquisite trajectory becomes a Sudoku puzzle where half the numbers are lies. Engineers mutter about B-plane targeting and turning angles while the object merrily cruises on, uncaring. Back on the ground, even perfect geometry on paper can be sabotaged by real weather and fake weather. High-thin cirrus elevates background and imitates poor transparency. Sahara or wildfire dust turns your flat fields into abstract art. The Milky Way is another kind of weather. Crowded star fields raise false positives in moving object pipelines and contaminate aperture photometry with blended neighbors. Deep stacks help, but they also average away rapid changes you hoped to catch. If geometry is the bouncer, the sky is the club's sound system. When it hums, your data sing. When it doesn't, you're dancing to static. Workarounds exist. Solar coronagraphs can catch low elongation activity if the object strays into their fields, offering a front-row seat at perihelion that ground observers lack. Small, agile telescopes fill gaps left by oversubscribed giants, hopping on targets of opportunity in the 20 minutes of nautical twilight where the big domes won't bother. Polarimetry can be more forgiving of bright skies than broadband imaging, teasing out dust properties when flux measurements saturate with noise, and coordinated global networks can stitch together a 24-hour light curve by baton passing across longitudes, provided someone somewhere is awake, which, in astronomy, is a solid bet. But the honest truth is that orbital mechanics writes the program. Some interstellar guests will perform in prime time with generous elongation, dark skies, and slow, courteous motion. Others will slam dance past the sun while we squint from the parking lot. The art is to build playbooks in advance, pre-scheduled cadences for every elongation and phase angle, scripts for switching filters when the moon muscles in, arrangements with multiple sites so no single cloud ruins the week. When the geometry finally smiles, you don't improvise, you execute. Next, we'll pivot from the tyranny of angles to the promise of signatures. What kinds of techno-hints we could realistically detect? Radio pings, laser ticks, polarization oddities, and how to rank them without turning every cosmic hiccup into a press conference. If it blinks prime numbers at us, that's either ET or a very nerdy comet. The good news, engineered things leave fingerprints. The better news, we have instruments that can dust for them. The challenge is to separate designed from merely dramatic. without mistaking our own electronics for aliens with a fondness for AM radio. Start with narrowband radio, the city workhorse. Nature is chatty across broad swaths of spectrum, thermal noise, masers, synchrotron, so a signal squeezed into a few hertz stands out like a laser pointer in fog. A proper search grooms the data with 3 hairbrushes. Drift correction for Doppler acceleration. The frequency won't stay put as the object and Earth dance. 2. Multi-beam on-off tests to veto terrestrial RFI. If it appears in every direction at once, it's the parking lot, not Proxima. And 3. Coincidence checks across independent telescopes within light time windows. A beacon worth printing t-shirts over will be stable, repeatable, and obey celestial geometry. It turns with the sky, not with your microwave. Broadband bursts are trickier, but not off the table. Think fast radio burst style envelopes or chirped sweeps. Natural plasmas can do wild broadband things. The discriminator is structure. A burst with engineered hallmarks might show constant dispersion-free arrival, or a deliberate artificial dispersion, precise repetition cadences, or polarization purity that laughs at interstellar Faraday rotation. We quantify with Stokes parameters I, Q, U, V. Natural clutter scrambles Q, U, V with frequency and time. A transmitter can keep one mode unnaturally clean, like a lighthouse, insisting on linear polarization at a fixed angle, despite the cosmos's best efforts to twist it. Lasers are the optical cousins of narrowband radio. 2 search modes dominate: continuous wave, CW, and pulsed. CW hunts look for impossibly thin spectral spikes. Nanometer? Not good enough. We mean picometer-level wiggles, riding on otherwise smooth continua. Instrumentally, that suggests high-resolution Echelle spectrographs and notch filters calibrated with laser combs to tame instrumental drift. Pulsed searches chase nanosecond flashes with photomultiplier arrays or single photon avalanche diodes, cross-checking multiple detectors to slay cosmic rays and airplane glints. The tell is simultaneity, coincident photons across independent channels, and recurrence. The same pulse train returns when the object does. If the pulses walk in prime intervals or binary framing, the nerdy comet hypothesis retires early. Polarization oddities sound esoteric, but are wonderfully nosy. Dusty comi yield polarization that flips sign near a small phase angle and follows smooth laws with wavelength, engineered surfaces, smooth dielectrics, metal foils, multi-layer films produce Fresnel-style polarization curves with sharp angle dependence and high degrees of linear polarization at specific phase angles. If we map polarization versus phase and get a curve that screams flat plate, we don't jump straight to sales, but we do start asking whether regolith can fake a mirror. Structured light curves provide another lane. Natural rotators give sinusoidal-ish modulations. Tumblers add beats and drift. A machine might prefer clockwork, crisp, repeatable features at fixed rotational phases, knife-edge occultations as booms pass, micro-eclipses from lattice ribs, or glints with timing that barely wanders over weeks. We stress-test structure with periodograms, wavelets, and phase folding. If the waveform survives different filters, apertures, and observatories, it's not an instrument prank. If it also lines up with predicted facet orientations from a simple shape model, congratulations, you've moved beyond potato. Unnatural material spectra is a mouthful. Think reflectance that looks engineered. Natural ices and rocks paint broad, blended bands. Manufactured stacks can carve sharp reflectance edges, flat plateaus, or interference ripples, thin film effects across contiguous wavelengths, a spectrum that stays flat as a table from blue to near IR, despite phase angle changes, and then shows a crisp thermal cutoff inconsistent with any plausible albedo-emissivity combo, hints at coatings. Add specular glints repeating with rotation and polarization angles, aligned with a presumed facet plane, and geology starts drafting concession speeches. All this only matters if you beat the gremlins. RFI is the final boss for radio. We quarantine suspect frequencies, log local emitters, and demand verifiable drift rates consistent with celestial dynamics, not the ceiling fan in the server room. In optics, we wage war on satellites, cross-match glints with orbital catalogs, require dual-site concurrence, and use rolling shutters or frame transfer to nail microsecond timing. For spectroscopy, we model telluric lines, instrument fringing, and scattered light mercilessly. If a spike sits on a detector column defect, it doesn't get to be a beacon. A ranking system helps keep pulses steady. Imagine a techno-signature confidence ladder. Single site anomaly. Interesting, almost certainly mundane. Repeatable at one site, promising. Still likely local/systematic. Multi-site, time coincident. Now we're talking. RFI, aircraft, mostly dead. Celestial geometry, locked. Appears with the target, vanishes off target. Physically self-consistent. Polarization, light curve, and dynamics tell one story. Predictive power, we forecast future behavior, and it happens on schedule. Instrument agnostic replication. Different hardware, same result. On-dependent domain corroboration. Radio plus optical, thermal, agree on the same engineered tail. You want tier 6 or above before you order banners? What about buried tech? Passive artifacts that don't transmit? Then dynamics and photometry carry the load. A ridiculous area-to-mass ratio with 1R quadride forcing, paired with mirror-like polarization and glints, sketches a sail. A radar cross-section far above rough body expectations at a given size hints at smooth facets. A thermal phase curve with ultra-low emissivity in narrow bands, think engineered radiators, is hard to explain with porous dust alone. None of these singly clinches the case. Together, they start to look less like geology and more like industrial design. Finally, culture. We pre-register our tests, publish raw data, and invite hostile replication. Every alien candidate must survive boredom, long, dull nights of control experiments where nothing fun happens. If the signature is still standing after that, you won't need hype. The plot will write itself, ideally in prime numbers. Next up, we'll borrow lessons from earlier interstellar guests, how first impressions misled us, what we corrected, and how to avoid déjà vu when the third visitor tests our new playbook. First pancake was lumpy, second was better. Third time we preheat the skillet. Our first 2 interstellar guests, 1I Oumuamua and 2I Borisov, didn't just wave from the doorway. They left sticky notes all over the lab. Reading them carefully is how we avoid reheating old mistakes with 3IATLAS. Start with Oumuamua, the 2017 surprise that arrived faint, fast, and already outbound when we found it. The immediate pain point was cadence. Discovery after perihelion meant we missed the warm-up act, where volatile species would have been easiest to spot. We were left with a sliver of time and an object dimming by the hour. The light curve showed a huge brightness swing, implying a dramatic shape or severe albedo mottling. But with sparse sampling and limited phase angle coverage, multiple geometries fit the data. Was it cigar-like, pancake-like, or a disco ball with commitment issues? The lesson wasn't pick a favorite. It was don't let geometry corner you again. Build phase angle diversity early, or be ready to live with degeneracies that mock your pretty shape models. Then came the delicate matter of acceleration. Oumuamua's trajectory displayed a small, persistent deviation from gravity-only motion. With meager signs of a coma, we leaned hard on models to explain a push without obvious exhaust. That vacuum spawned a garden of hypotheses, exotic ices, fragment with huge area-to-mass, fluffy aggregate, light sail-like sheet, each able to fit parts of the data with different knobs. The durable takeaway wasn't which one wins. It was procedural. If you discover late, you drive in the fog, and tiny systematics, signdoinding, color terms, solar radiation pressure estimates, loom large, moral, prioritize deep, multiband imaging and sensitive gas searches within days of discovery, when even whisper-thin activity would show. Waiting a week converts decisive tests into armchair debates. Oumuamua also taught humility about single-method stories. Photometry alone can impersonate spectroscopy. Dynamics alone can impersonate engineering. The most convincing narratives used cross-checks, e.g., tying light curve amplitude to plausible thermal inertia, or testing whether a required area-to-mass ratio would make the surface temperature evolution absurd. When independent domains converge, confidence grows. When they don't, you've found either a clue or a calibration gremlin. Multimodal or bust is the bumper sticker we should have printed in 2017. Enter 2I Borisov in 2019. Bless it, the cooperative guest who actually looked like a comet. We caught it earlier, with generous observing time, pre-perihelion. It sported a healthy coma and tail, letting spectroscopists do their thing without begging the signal-to-noise gods. We measured familiar molecules, saw dust behave like dust, and watched activity ramp sensibly with sunlight. That normalcy was a revelation. Interstellar objects need not be weird to be priceless. Borisov said, "Sometimes a postcard from another star looks like a postcard. Stop trying to read cryptic ink when there's legible handwriting." Also, with sustained monitoring, we watched compositional ratios evolve, something we couldn't do for Oumuamua. Lesson: persistence beats drama. A well-observed, boring object advances the field more than a late, spectacular mystery. Borisov also sharpened our data hygiene. With a bright coma, centroiding the nucleus gets tough. Gas and dust weight the light differently across filters, dragging your position around by subtle amounts. Teams that tracked filter-dependent shifts and modeled coma contributions ended up with cleaner astrometry and fewer phantom accelerations. That's the quiet craft. Put photometry, astrometry, and coma physics in the same room before you ask dynamics to adjudicate. Otherwise, the orbit fit explains what the pipeline introduced. A meta-lesson from both visitors was how to talk in public without eating our hats later. Oumuamua's mystique collided with headlines. Borisov's normalcy risked yawns. The fix is framing, emphasize testable predictions and planned observations rather than identities. Tomorrow, we'll check for CN at the sensitivity. If absent, we rule out X is stronger than it might be a sail, or it's definitely a snowball. Both cases taught that public wonder survives nuance. It just needs a beat to land. Scientists can be hosts and referees, but not if we promise touchdowns before the kickoff. Operationally, we learned to mobilize faster and wider. For Oumuamua, access to big telescopes was precious and late. Borisov benefited from pre-planned rapid response modes and a well-oiled alert ecosystem. The new standard playbook includes immediate multi-filter photometry to pin down colors and coma growth, narrowband comet filters if activity is suspected, early near IR for water and CO2, and radio for COHCN if feasible. Polarimetry joins the party early because it's robust against some sky conditions and gives dust diagnostics while everyone else is still wrangling exposure times. And crucially, we schedule phase angle sweeps and dense time coverage to kill period aliases before they breed. We also learned the value of archival archaeology, precovery hunts, diving into survey images taken before discovery, rescued both objects' orbits from ambiguity jail. For future visitors, teams now automate those searches across multiple archives with moving object-aware tools that don't get fooled by trailing. Every night you push the orbit back in time is a night you shrink uncertainties and stop hyperbolic versus parabolic food fights before they start. Finally, both objects reminded us to separate unknown from unlikely. Oumuamua sat in that tempting valley where exotic explanations glitter because common ones are hard to verify. Borisov sat on the plane where common explanations worked beautifully. The discipline is to keep priors honest and let data weight them, not the vibe of the week. When the third visitor arrives, hi, 3IATLAS, we should act like we've learnt our lines, catch it earlier, coordinate globally, diversify wavelengths immediately, archive RAID aggressively, and pre-register tests that could falsify our pet ideas. If the object behaves, we get a clean comparative sample. If it misbehaves, we'll have the instrumentation already pointed and the statistics already armed. Next, we aim past the dome and into the design lab, how to go from rapid response to rapid launch, sketching mission concepts that chase a fast mover on cruel deadlines without asking rockets to do magic tricks. Space missions are like pizza, fast, cheap, or good. Pick two. The universe picks one. When an interstellar visitor pops up, the clock starts shouting. You've got months, if lucky, between discovery and closest approach. And the kinematics are rude. High relative speed, awkward inclination, and a trajectory that refuses to swing past your preferred launch site at 2 p.m. on a Wednesday. Designing a pursuit is less grand tour and more grab-your-go bag. First decision, flyby or rendezvous. A rendezvous demands enormous del V to null relative velocity, often fantasy territory, on short notice. A high-speed flyby is feasible but unforgiving. Milliseconds per pixel and one bite at the apple. That choice cascades into everything else. Propulsion, navigation, instruments, shielding and comms. Rapid launch platforms are the backbone. One strategy is a standing interceptor bus, microsat or smallsat class, kept flight ready with a modular bay for a minimal payload. Narrow, wide cameras, a compact spectrometer, a dust counter, maybe a micromass spectrometer, if mass allows, off-the-shelf components/integration time, and standardized ground support equipment avoids bespoke headaches. Synthetic tracking on board, stacking short exposures in the direction of expected motion, helps acquire a target that's faint and ephemeris slippery. Autonomy is not a luxury here. Light time delays plus uncertain geometry mean the craft must retarget, refocus, and adapt exposure sequences without waiting for Earth to rubber stamp every tweak. Propulsion is a buffet where every dish has fine print. Chemical gets you instantaneous thrust. Great for making the window, terrible for sustained V budgets. Solar electric propulsion, SEP, offers sips of thrust over weeks to months, ideal for gentle plane changes and tightening intercept geometry, if you have time to spiral and power to spare. Kick stages, solid or storable, can bolt onto a rideshare to jack up C3, escape energy, post-injection, turning a pedestrian launch into a respectable interceptor. And then there's the solar sail gambit. Park a sail in an inner solar system orbit, soak up momentum for months, then cant the attitude to sprint toward the target when the ephemeris gels. Sails trade propellant for patience. If you've pre-positioned one, you've effectively bought time in advance. Piggybacking is the opportunist's friend. It's rideshare to a generic heliocentric drop-off, e.g. an Earth escape or geo-graveyard departure. Coupled with your own kick stage, can position a tiny interceptor in a ready-to-pounce drift orbit. Alternatively, hitch a ride on a mission already heading sunward and release a daughter probe at the right node. Small probes can also loiter at L1, L2, or in Earth-leading/trailing orbits, where modest burns reshape their paths quickly. Think of a distributed picket line, several seed craft pre-deployed, any one of which can become the chaser when a visitor appears. The flashy, terrifying option is the O-berth maneuver, burning a big chemical stage at perihelion to multiply its effectiveness. Brilliant because dull V there buys you outsized energy. Brutal because surviving a sun-skimming dive is an engineering dare. Your stage needs thermal protection, ablatives or ceramic tiles, autonomous guidance at eye-watering velocities, and a burn window measured in minutes inside a furnace. Miss your timing, and you've converted a booster into a fond memory. Still, A pre-staged hot rod stage on an inner solar loop could transform a medium launcher into an interstellar sprinter without inventing new physics. Instruments must match sprint reality. Imaging needs two lanes, a wide field finder to acquire and maintain lock, and a narrow, fast telescope for science. Short exposures, large pixel wells, high frame rates, and a shutter that won't cry at 15 kilometers s cross-track rates. Spectroscopy favors slitless or push-broom designs to tolerate pointing jitter, or ultra-simple filtered imaging to sample key bands without finicky alignment. For dust, aerogel collectors can snag grains at km/, but at extreme speeds, fragmentation and heating complicate interpretation. At minimum, fly a Whipple shield sacrificial bumper plus standoff to keep the spacecraft from becoming an unplanned meteor. A postage stamp plasma package, Faraday cup plus magnetometer, reads solar wind context and ion tail structure in situ. Small mass, big science. Even a totally normal space snowball is a postcard from another solar system. And postcards carry information: where it was printed, what ink they used, and whether the sender spilled coffee on it. A natural 3IATLAS would still be a once-in-a-decade reality check on how planets and smaller bodies are made across the galaxy. First, composition is cartography. Ratios among H2O, CO2, and CO act like latitude and longitude for protoplanetary disks because each volatile condenses at different temperatures. A high CO-H2O mix hints that icy grains assembled beyond a far-out CO snowline, perhaps in a cold outer belt around a modest star, water-rich with little CO points closer in. Add methanol, ammonia, and simple organics to the tally, and you sketch not only where the grains formed, but also how long they basked in ultraviolet light or simmered in mild heating. We're not guessing, the molecules are thermometers with labels. Dust minerals write the footnotes. Crystalline silicates imply episodes of heating and radial mixing, material once near a young star's furnace carried outward and then locked into planetesimals. A 3IATLAS shows a high crystalline fraction. That argues for energetic transport in its birth disk. A dominantly amorphous makeup tilts toward gentler assembly. Grain porosity and size distributions do double duty. They betray whether the building blocks clumped softly, streaming instability and pebble accretion, or got ground down in rough collisional neighborhoods. In short, rock texture is an eyewitness to the traffic laws of another planetary nursery. Dynamics turns the postcard over. An interstellar object has to be kicked out by migrating giants, resonance chaos, or close stellar encounters in a birth cluster. The space density of such visitors, combined with their typical speeds and directions, calibrates ejection efficiencies. See enough boring interstellar comets, and you can backsolve for how often young systems do violent rearrangements like the ones our own giants likely pulled off. It's planetary sociology via census. Lots of runaways mean many households with rowdy teenagers. Read Migrating Gas Giants. Size matters, and not for vanity. If follow-up photometry and thermal constraints place 3IATLAS in a particular radius range, that data point lands on the size-frequency distribution of ejected bodies. The slope of that distribution, steep or shallow, tells us if most solids formed as a few big chunks or as swarms of smaller ones. That, in turn, feeds formation models. Streaming instability loves to make 100 kilometers-ish seeds, while protracted collisional growth leaves different scars. One interstellar snowball does not a histogram make, but 3 do more than 2, and the trend line has to start somewhere. Isotopes take us from where to how. DH in water and 15N, 114N in nitriles can diverge from solar system norms, flagging colder or differently irradiated environments during formation. Match our object's DH to values seen in comets from our Oort cloud and Kuiper belt analogues, and you'll strengthen the case that chemistry converges across disks. Find a systematic offset, and you've just constrained disk temperatures or cosmic ray fields in a foreign nursery. This is comparative planetology, with lab precision, not poetry, just numbers that move model sliders. Natural also answers, how long can stuff last out there? Interstellar residence exposes small bodies to cosmic rays and sputtering for millions of years. If we see, for example, surface devolatilization, but intact deeper layers, inferred from activity turn-on distances and production curves, we've measured a survival timescale for ices on the interstellar highway. That pins down how much organic cargo such bodies could realistically deliver if they wander into young systems later. An ingredient list for panspermia debates, minus the hand-waving. No need to argue if the fridge stayed cold. The coma will tell us what spoiled. Speaking of delivery, a natural interstellar comet is a courier service demo. Even if no biology hitchhikes, organics and prebiotic molecules almost certainly do. If modest numbers of such bodies thread star-forming regions or young planetary systems, they become a background drizzle of complex chemistry, seeding disks with extra carbon chemistry just when rocky worlds are assembling. That's not sci-fi. It's an exchange program run by gravity. Think interstellar composting. Low-key, widespread, chemically meaningful. Natural outcomes also calibrate our instruments and strategies. If we execute the perfect multi-wavelength campaign, and everything lines up with ordinary comet physics, we've stress-tested the pipeline in exactly the environment where future weirdness claims will be judged. Knowing that our spectrometers, polarimeters, and tracking photometry behaved under normal conditions gives us credibility when we later shout anomaly. Baselines are not boring. They are the ruler you measure surprises against. There's a galactic ecology angle too. The velocities of interstellar objects relative to the local standard of rest and their arrival directions trace stellar kinematics, streams, moving groups, the suns meander through the neighborhood. If 3IATLAS's inbound vector matches known groups, we can sometimes backmap to plausible birth regions, or at least to the kind of stellar populations, red dwarfs, sunlikes, that preferentially donate debris. Every trajectory is a breadcrumb for dynamical archaeologists. And then there's humility. A natural verdict forces us to sharpen natural explanations, rather than reach for exotic ones prematurely. If, say, a subtle non-gravitational acceleration shows up and collapses neatly under a CO-driven model with reasonable thermal lags, we've not only explained 3IATLAS, we've upgraded our manuals for comets in general. That improvement travels to active asteroids, to distant centaurs, to the dust budgets of debris disks we observe around other stars. Finally, wonder doesn't need a circuit board. A natural interstellar comet is a message in a bottle from a nursery we'll never visit. We can read its chemistry, weigh its dust, time its breath, and fit its path, all with photons caught by mirrors under a cold night sky. That alchemy, turning faint light into a family history, remains one of science's neatest tricks. If 3IATLAS is just a comet, then just means we learned how common our story might be. Next, we'll open the door to the spicier case. If it isn't natural, if hints of design stack up, what motives, ethics, and first steps make sense when the universe finally leaves hardware on our doorstep? Step 1. Don't poke the alien drone with a stick, especially not on live TV. If 3IATLAS shows traits that demand design, disciplined thrust profiles, mirror flat facets, intentional signaling, our playbook shifts from observer rock to behave like a civilization. The first move is to characterize without tampering. The second is to decide whether any action beyond watching is justified. And the third is to make sure we don't learn the wrong lesson faster than we learn the right one. Consider 3 motives with 3 very different footprints. A quiet sentinel passes through to taste fields and chemistry, leaving only refined inertia and restrained glints. You learn from its restraint. A beacon tries to be noticed. Tight band transmissions, deliberate optical ticks, geometric reflectors, designed for easy photometry. You learn from its generosity. A relic says nothing but looks manufactured. Composites, lattices, coatings that scream optimization. You learn from its bones. In each case, our responsibility is the same: preserve provenance, reduce conjecture to testable statements, and keep the evidence chain unbroken. Signals get raw dumps plus independent captures. Dynamics get multi-pipeline reductions. Materials, if any dust intersects our detectors, get logged with custody records, strict enough to make a museum registrar blush. Contact, if it happens, should follow a ladder that prizes reversible steps. Listening is free. Passive optical modulation from Earth, say sunlight shutters in mathematical rhythms, is low risk. Directed transmissions are last, not first. Any attempt to illuminate the visitor, high-power radar, LiDAR, laser, is evaluated like a medical procedure. Indication, dose, alternatives, consent assumptions, and a debrief plan. The ethic is simple to say and hard to keep under pressure. Curiosity is not a license. It is an obligation to minimize harm while maximizing information. Message design has to respect time and context. If you send, you encode redundancy that survives compression loss. Frame it in shared physics, spectral lines, simple arithmetic, celestial landmarks, and avoid payloads that could be executed as code by a naive receiver. That goes both ways. We sandbox anything we decode, because the first practical test of wisdom is whether we can resist double-clicking the cosmic attachment. For semantics, we borrow from semiotics and linguistics. Layered messages, beginning with numbers, then geometry, then diagrams of measurement standards, and only then anything about biology or culture. The goal is mutual bootstrapping, not a TED Talk hurled across space. Governance must be multinational from day one. An international custodian group, scientists, engineers, ethicists, diplomats, and public advocates, publishes schedules, allocates telescope time, and records every action in a public ledger with immutable hashes. No private embargoes, no unilateral celebrity announcements, no secret knobs. If a nation or company has unique assets, great. Those assets operate under jointly agreed protocols. It isn't romance to insist on this, it's risk management. Monopolies warp incentives. Transparency stabilizes them. Risk is layered, physical, informational, and societal. Physical risk is obvious: approach trajectories, dust sheaths, unknown fields. We set standoff distances with margins, use non-contact diagnostics, and design any interceptor with sacrificial shielding and fail-safe attitudes that default to retreat. Informational risk is what we reveal inadvertently: detailed RF fingerprints, software stacks, even rhythms of our power grid encoded in sidebands. We compartmentalize telemetry, strip identifying features where feasible, and publish only what the science requires. Societal risk is the turbulence of meaning. We route that energy into education, not whiplash. Regular bulletins with plain language summaries prevent rumor vacuums, and corrections are flagged boldly rather than buried. Law and ethics will lag unless we accelerate them. Appropriation is out by treaty. Stewardship is in by necessity. If fragments become accessible, we debate whether sampling qualifies as respect or vandalism. Dead tech may seem fair game, but context could matter. Inscriptions, alignment behaviors, even long cycle duty periods we haven't waited out. A moratorium on invasive actions while we complete a defined observation program, clocked by true anomaly, not impatience, keeps us honest. If intervention is ever proposed, it should pass tests that sound like a clinical trial: clear scientific aim, minimal invasiveness, peer review, pre-registered procedures, and a public post-mortem of outcomes. Motives are interpretable, but not inferable from one datum. A sentinel might ignore us, a beacon might be a classroom exercise, a relic might be a memorial or trash. We therefore commit to predictive humility. We publish what each hypothesis would imply next week: spin locks, pulse cadences, thermal behaviors, and we score ourselves on whether those predictions land. Theories graduate by keeping appointments, not by collecting retweets. Culture deserves a seat at the console. Artists can visualize what the numbers describe. Historians can compare our moment to past first contact myths. Philosophers can map the boundary between caution and paralysis, and theologians can help communities integrate the news without humiliation or hype. That's not window dressing. It's resilience engineering for a species that learned in public. Economics will knock on the door. We keep it in the waiting room. No advertising rights, no private salvage claims, no naming games until the basics are settled. If spin-offs arrive, better detectors, cleaner coding practices, new consensus tools, those are dividends of sobriety, not trophies of conquest. Meanwhile, we harden the information commons, open repositories, mirrored globally, classroom-ready datasets, and citizen science portals that let people touch the evidence rather than argue about a headline. In the end, ethics is a habit, not a press release. We cultivate it with drills, tabletop exercises for signal handling, dry runs for data release, red team audits for our pipelines, scenario war games that stress test governance when sleep is scarce and attention loud. Practice now so that, should design reveal itself, we meet intention with intention. Next, let's shift from words to visuals, prompt mode to craft cinematic images that help audiences grasp these forks in the road: the silent sentinel, the bright beacon, the careful council chamber, and the restrained spacecraft holding station at a cautious, civilized distance.